Hello and welcome to the introductory video to Excalibur. I recorded this previously on Twitch, but I lost the recording because Twitch only holds on to recordings for a few weeks. And so I'm re-recording this to preserve the introduction I made. So what is Excalibur? Excalibur is just a name I picked at random for this new project I want to start, where I'm building my own web server and service framework from scratch, mostly using C++, and I decided that I would build it and develop it while live streaming it or recording it if I can't live stream. And I want to make this web server cross-platform, so it should run on Windows, Mac OS, Linux, etc. I'm going to reuse some custom utility libraries I developed in the past so that I don't have to rewrite everything from scratch. I developed them in the past for some other hobby stuff, for things such as networking, data structures, string manipulation. I'm also planning to reuse some open source libraries for some of the more complex things like transport layer security and compression. But for the rest of it, it's all going to be written from scratch, hopefully live. And I have a public notebook that I'll link to from both Twitter and YouTube probably. And it looks like this. And it's going to document the whole process. So things like initialisms and acronyms that I use, I'll have links to them describing what they are. All the terminology. So decided to list all the terms that I use that aren't common knowledge. I might miss a few if I'm so used to using them that I don't realize they're programmer terms. But maybe people will let me know that I have some terms missing. So this isn't intended to be a complete replacement for the web. You can always look stuff up, of course. I just wanted to have one place where two things. I wanted to summarize the terms I use in describe them in my own words, so that if the terms might differ from common use, you can see how I use the words. Also, it's just a more convenient place so that you don't have to Google search if you just want to quickly look up what does some word mean. I'll have some project-specific words. So the first one I made was Excalibur, just to name the project something. And why am I listing terms and initialisms, acronyms, and project-specific names? Well, I think names are important. They help avoid ambiguity. So I'm going to list them all. Also, in this name section, I have the names of some common design principles, some common design patterns. I try to follow these both to make my code easier to read and to help me avoid design mistakes and traps. And also I can use the names of the patterns and principles so that people get an idea of how my code is organized in the first place and what I'm trying to get at. Also, I'm going to have a section here called references where I list all the tools I'm using, and probably you'll have to Google search them to get more information if I don't provide links here. Also, I'm going to have a list of the standards documents. So a lot of this work with web server is going to be based off of internet standards. Internet standards are mostly published as RFCs, or requests for comments. Publicly available free documents that describe all the protocols and requirements for the internet. So with all that background information set up, let me go over what goes into a web service framework. So the key components of a web service framework are the web server itself, resource providers or services, messages between server and client, and I'm also going to throw in WebSocket, which is a convenient mechanism for doing real-time message-oriented two-way communication between a service and a client. So the essential protocols and standards that we're going to cover, back to the list here. We're going to start with URI, or Uniform Resource Identifier, because that's a smaller standard that we can handle right off the bat and get pretty far in. without too much time. That's going to be useful for our web server, which is going to implement a big part of this HTTP or hypertext transfer protocol, which is the underlying protocol of web servers. It's also to be used a bit in WebSocket protocol, which is an extension to HTTP for the two-way real-time stuff. And after we get URI squared away, in preparation for doing the main web server, we'll set up the internet message format, which is a protocol or a format that's shared between email and web traffic. So messages between web servers and clients follow this message format, so we're going to implement that. And one thing that's needed for that is Unicode transformation format, or UTF. And that's in order to allow messages to use all sorts of different character sets, not just ASCII, but international character sets as well. And it's generally a good thing to do nowadays for text that's going to need to support international character sets. So some areas that I still need to research that I don't have set up to go yet are transport layer security for making the web server secure, so I'll have to look into that. Compression, for example, zlib or gzip. I haven't looked into that very much. And doing proxy role for a server, I haven't looked that up yet. But otherwise, I've already reviewed all of these standards, and as I go along, I'll mention the key elements and requirements of each. So let me describe to you the layout of the code. So at the very top level, this is what I call a solution or a workspace. And it's going to have all the projects that we're going to build together, all the components. And some of the key elements of the overall workspace, and also some of the same files you'll find in each project, are the README file. README is there to describe what the thing is. And I like to use this markdown syntax because it's really easy to generate a PDF. If I do this right, we can preview it in Visual Studio Code. And if you check your code into GitHub and make this README file checked in with your code, it will show up when you browse your code in GitHub as well, so it's really nice. Then for the main top level workspace, we have this main XML file. And this is used by the tool I use to handle version control. So the top level workspace is in a Git repository, and I want to set up all the individual projects or libraries to be in their own Git repositories. Some people refer to this as the multi-repository mode or discipline. Other people prefer what they call mono-repository, or putting everything into one Git repository. I happen to like the multi-repository, multi-repository viewpoint. So I have what I call a manifest, or an XML file, that describes the names, paths in terms of a Git URL to actually get the component, and then what branch and version control to get it from. And then in the case where I want a specific version of a component, I'll pin it or lock it down to a specific revision. So I use a tool called Mugit, or multiple Git, that I wrote to help assist in cloning and managing and tracking the status of all the repositories in the workspace. So right now we're starting out with 3. There's the main top level one. There's the URI, which I just set up the bare bones structure for it. And then we're leveraging Google's test framework for C++. Get into that when we talk about unit testing. Another tool that I use as a segue into the next file is CMake. CMake is a tool for constructing build systems. And the syntax is a bit hard to read and hard to learn, but there are a lot of advantages to using it. For example, with this one description, I can generate build system for Visual Studio, or for Xcode, or for GNU Makefiles, or any other kind of build system that CMake supports. So we describe in CMake's language how the project structure is set up and what to build and how. And then we ask CMake to construct the build system, and then we use the build system to build the code. So at the top level, I can briefly go over some of this stuff. So we're using version 3.8 of CMake. We're using C and C++. We're by default setting modern versions for C and C++. And there's a bunch of setup stuff I'll skip for now. But down here, we're pulling in Google test. This add subdirectory pulls in a subordinate CMake description file for the individual components. So this one's pulling in Google test. This one right here is pulling in URI, and we're going to add more add subdirectories as we go on to add things like the web server, the WebSocket, UTF-8, and other things. All right. So last two of the 5 files at the top level, git ignore is used with git, and we're going to tell git through this file about the directories and files that we don't want to check into this top level or git repository. So right off the bat, the 2 subordinate repositories, they're separate, so we don't want them to be pulled into the top level repository. They're kept separate, so we ignore them at the top. Then also the build folder. This is constructed by CMake, and that's where all of our build products go. If we had other files, like temporary files, or files we are sure we never want to check in, we would add them or add patterns that match them to this file. Last but not least is the editor config file. I learned about this recently. This is a convenient way to tell complying or not complying supported editors, and Visual Studio Code is one, about the preferences that we have for editors for this workspace. So basically saying we prefer editors to use UTF-8 character set, so we can have international characters, copyright symbols, etc. And we prefer that in our code we're going to indent by 4 spaces, and we're going to indent using spaces and not tabs. And when we save the source files that we're editing, each time it's going to remove any white space on the end of the line. That's, you don't need that. And then if it's missing, add a new line at the end of the file. That's pretty much it for the top level. As you can see, the top level doesn't really have any code. It might have code in the future if I make a new library and it doesn't have its own repository or home yet. It might temporarily be held at the top level. But otherwise, all the code is generally going to be in the subdirectories. So Google test we're not going to really look at, because just assume that it works. And we'll get into that one when we talk about unit tests. URI, I'm going to open that up and show the typical structure of a single library or app. And all of the libraries and apps we're going to develop are going to have the same structure. So include is our public interfaces. They're generally going to be just header files. And we have another level that has the same as the top level. This is a convention that helps when we set up our include paths. That's so that when we include the URI.hpp, we'll be doing it by doing a #include URI/URI.hpp. That's so that we can relocate this URI anywhere. We can install it in the system libraries. We can keep it where it is. And it keeps the structure. We can also, if we had a more complicated component, we might have several different subdirectories for header files. And so that having this extra level here lets us organize our header files in subdirectories. SRC, or source, is all of our implementation. Test is our unit test, which you can think of as a sub-component of itself. So it has the same kind of structure. If it had an API, it would have an include. Unit tests usually don't need an API because they're apps. They're not used by other things. They're top level, right? So we just have source. And in CMake lists, just like at the top level, we're going to see them here, both this one for the URI library itself and this one from the unit tests. And this is pulled in from the top level CMake list. And here's where, with this add library, we're defining that we're going to build a static library. And we're listing the source files here and the header files here that we're going to pull into this library. Target include directories is going to let other projects know where to find our header files. This is how our include path is set up automatically. And then the app subdirectory test is going to pull in our unit tests. Unit tests are adding an executable or a program. The program consists of our tests, and then we're going to link with both the thing we're testing and then with gtest main, which is Google Test wrapper that provides the main program. The way it works is Google Test has the main function, and through the linking process, it discovers all of the tests you have defined, and the main basically lets you run all the tests automatically or run just the tests that you want, depending on what you put on the command line. So one other thing in the CMake this file is this add test. That's if we use the ctest tool, which allows us to run all of our tests from the command line without specifying each one after another. We can just run them all. Sort of a top-level sanity check that all our tests are still working. All right, so let's go to the command line here. And we're going to go to our projects, Excalibur. And let's see if I already have a build. I already have a build, so let's move it. And here's the process that I follow. I'm just setting up a workspace. Make the build directory, change to it, then we run cmake to generate the build system. Specify the build system generator that we're going to use, and then architecture. So we're going to 64-bit. Give the path to the top-level CMake list. CMake will detect the versions of the tools that we have, and it does some checks to see that we have all the tools we need. And it will create, since I asked it for Visual Studio, it'll create a top-level Visual Studio solution file, and then individual subdirectories will have the project files that we're generating. There are also some boilerplate standard project configurations that CMake sets up that we're not going to use too much. They're just convenient things like in the install project. You could run it to install your stuff. You had install rules, run tests to run all your unit tests if you want to do that. But we're mostly going to do the command line today. So to build with CMake, just do CMake and then -- build. Give it the relative path to the build directory, which we're already in, and config debug. It's going to use ms build, which is the command line executor that goes along with Visual Studio. It's going to build everything. Then, like I said before, with the add tests, it allows us to run ctest, give it the same configuration name, and it runs our unit tests. And that's just a very binary, like pass or fail. If we wanted to see individual test fixtures and tests inside of the unit test runner, we have to run it directly. So to do that, you URI test and the config. No, it's URI/test/debug/URI test. Here we get the output from Google Test. And right now I only have one test called placeholder, but if we had more tests, it would show run and then result for each one, and how much time it took for each one. That's how we build and test on the command line. So we can also open the solution file. Alright, that failed because my license to Professional Edition of Visual Studio expired. So I'm going to uninstall that and install Community Edition and then try again. Alright, done installing Community Edition, and let's try again. So when we launch our solution file, we get, because of the instructions I set up in CMake, we get our unit test project showing up under tests, and then under libraries, we have our library, and then we have Google Test main wrapper, and then Google Test, the core of it. So I think I already did this before, but if you set that as the startup project and hit Control F5, it should run our tests. I'll do a lot of my development from Visual Studio because I'm used to the editor, but we should be able to edit either here or in VS Code. See the same thing. So a little bit about the structure of a component. So URI is the component for what is it exactly? It's a uniform resource identifier. I always screw that up and think it's universal resource, but it's uniform resource identifier. And right now it's composed of just one class called URI, and we'll see that header file. And a lot of the classes and libraries I write will follow the same kinds of patterns. So the principal class of a small component will usually have the same name as the component's library. So URI class goes into the URI library. And for the namespace, I usually make the namespace match the name of the library. So in this case, since it's a small library, named after the class inside of it, both the namespace and the class are the same. I might drop the namespace in that case if I know there will never be anything else but that class. Otherwise, it's a little bit redundant because you have to say URI : URI whenever we use it. But just for now, I'm showing the general structure of from small to large libraries, so I wanted to keep the namespace. So we're including the memory part of C++ standard library because we're using a unique pointer. Now, this is referred to as the PIMPL, or the pointer to implementation pattern. I should probably add that to my list of patterns in my notebook, but the idea is that in the header file for the library or for the class, we don't want to expose the actual implementation details, but in C++, when you declare a class, you need to declare all of its properties, even the private ones. So we separate implementation from the interface by declaring an opaque type impl, just as a struct with no definition yet. And with unique pointer and shared pointer in the C++ standard library, you can use that opaque type as the argument to a template, and users of the header or the library can still use the class without the compiler actually knowing the real definition of impl from the perspective of the interface. The implementation file, though, we're going to give a body or contents of that impl structure. So then a couple of other standard things. Usually you'll have a constructor, like the default constructor here. And then in a separate section, I like to put what I call lifecycle management. That's these 5 standard methods, and sometimes it's referred to as the rule of 0 or the rule of 5, modern C++, because these kind of fit together. If you need to have one of them, you should define all 5. If you don't need any of them, you can skip them all. And I'm using this other feature in modern C++ where you can specifically delete or declare that there is no body, or that it can't be called. But really briefly, those 5 methods are the destructor, the copy constructor, the move constructor, the copy, copy assignment operator, and the move assignment operator. So for our URI class, we're saying basically it can't be copied or moved, but it can be created and destroyed. The idea behind that is we're going to make it so that you don't actually copy or move URIs, you just make a new URI whenever you need one. I might change my mind later, and if I want to allow move and copy semantics, I would remove the equals delete and then define a body. So the implementation contains all the bodies. Right now we just have a placeholder for where we would put details of the implementation, and then we actually have bodies for the destructor and the default constructor. The default constructor is going to make the implementation structure. Generally that's all that it has, although sometimes you'll have some default construction initialization steps here. And this trick here, equals default in the implementation file, allows us to, in the interface, just declare the destructor but not actually give any implementation. And in the implementation, we can say, well, we don't actually need anything other than the default, so it's a shorthand for having an empty body. Now the reason why I don't put that in the header is it's a little bit of a tricky detail with unique pointer in that unique pointer is fine when you for using an opaque type as long as the constructor and destructor are external objects, not inline. If I were to take that equals default and put it here, it would cause it to not compile. And it's a little of a tricky reason. Maybe I'll make a video about that at some point. But I kind of am used to setting things up like this to start with, and if I need copy move semantics, I'll remove the equals deletes and put a body in the implementation. I need extra constructors to put them here, and later what we'll see is we'll be adding a methods section, or not well, actually what am I thinking? There already is a method section. We'll add other methods here, like do this, and usually I'll put a comment before every method and property in a class, and these comments start with 2 asterisks, and that's a notation used by Doxygen for automatically generating documentation out of header files. I don't typically do that, but if I were to make a library and then want to have a reference guide, HTML or web page about it, I would run Doxygen. It would create most of the web pages out of the notation that I write here in the header files. Let's say this function does something, and then following the Doxygen notation, if you have parameters, you would say something like parameter foo, this is the thing, whatever. If you had a return value, you'd say return something else. That's if you have a actual return type here. If you don't have a return type, if it's void, you skip the return thing. If you don't have any parameters, you just do that. So anyway, that's where we're going to be putting our public methods later. And again, this declaration, this header file, is the public facing interface to the URI component. And so it won't have anything about the private implementation other than this sort of a stub or a reference that's only resolved at runtime. And it's the structure, again, it's opaque. We can add and remove and change things in it and not mess up the interface in any way. Implementation is going to have the details of that impl structure and then the bodies of any methods and constructors and anything else that we add. So all of the projects are going to follow that sort of basic outline. Let me show you what a unit test looks like. So you don't actually have to write much for a unit test if you use Google Test, because Google Test generates the main function for you, generates the code that finds and runs all of your tests. All you really need to do is provide the tests themselves. And so it's through macros, and the simplest is just test. You give a suite name and then a name for the test. Then your test is going to be composed of assertions and expectations. So here we're just a placeholder that true is true so that the test always passes. We did something like this and built. Do the build again. Oh, that happened because I switched from professional to community. Let me show you what I'm going to do to fix that. Move the build, make the build directory again, repeat our generator. And we can build again. There we go. Just to show you an example of a failing test. Now when we run ctest, it's going to say it failed, but not really say why. To see why, we're going to have to run the test individually. Now we see that that particular test failed, and it shows us the file name and line number, where it failed, and then what it was expected and what the actual value was. So did I close Visual Studio? I did, didn't I? Let's open it again. And set that as the startup project. You only have to do that when you generate or regenerate the build system. Visual Studio will do that sometimes. Even if you build it with MS Build, Visual Studio thinks it's not up to date. But it generally doesn't really do much other than relink. So relinked, we ran it, see the same test failure. Go back and fix that. Oh, it wasn't in the module, it was in the test. I think I was editing in VS Code before. Now we're back to Visual Studio. We're put it back to true. Now our test is passing. All right. I think that's about it for the intro. Let's see if I missed anything. I have a cheat sheet here off to the side. Went over the project structure, top level files. Yeah, I mentioned it, but I didn't really go into detail about Git. So I'm using Git for the version control system and mugit, which is a tool I wrote on top of Git to manage some multiple repositories. So for running CMake and running testers and normal programs, I use just a built-in command prompt for Windows. But for Git, I like to use the environment that NGW Git provides, including setting up my authentication key for me so I don't have to keep typing that. Do Git status on the top level, it just tells me the status of just the top level. Mugit status, though, will show me the same thing for the root, and also it'll check the individual subdirectories. So this little hat here means that I have pinned Google Test to a specific revision. I'm doing that because I'm using something past the last release, but that hasn't been released yet, and if I were to just take the very tip of the master branch, it could break, and I don't want to get disrupted by that. So I just picked a version of Google Test that worked. So if I go back here and change that back to false and run my status tool again, now it shows the M for modification. To actually see more detail, we have to go into that directory and use git. Tell us that that file changed, and do git diff. It'll show us line was and what it is now, and I can reset if I want. Go back and run mugit again just to make sure. We're back to no changes. You can see when I switch back to Visual Studio, it says that it changed. Just reload, yes, now it's back to true. Alright, anything else that I forgot to cover? I think that's about it. So hopefully you got something out of this introduction. Maybe you were watching some of my work mid-project and you're curious about how it started. You wanted to get some of the fundamental starting points. Hopefully it wasn't too boring. Anyway, please feel free to access this public notebook. I'll be keeping up to date, hopefully, all the standards documents I'm using, all the tools, all the design principles and patterns, and I do need to add the one about pimple pattern. I'll add that in a bit. Terminology, if I invent my own terms, I'll put them here under project specific. All the acronyms and initialisms, and there'll be other pages and other sections that, as I go along, hopefully document everything I learn and everything I do with this project. And thanks, hope you got something out of it, and be chatting with you soon, maybe.